Greetings TA and professors, we are Jun Lin and Yan Yu, and today we'll be presenting on our SC1015 mini project. Our mini project is based on the mushroom classification dataset sourced from Kaggle as well as over 300 images of random mushrooms sourced from the internet. This dataset includes descriptions of hypothetical samples from 23 species of guild mushrooms in the Agaricus and Lepiota family mushroom taken from the Audubon Society Field Guide to North American Mushrooms, and these are the contents that we'll be going through in this presentation. We'll start off with our motivation for choosing this dataset before moving on to our exploratory data analysis, our machine learning models, AI model, applications for our findings, and finally our conclusion and evaluation. Why mushrooms? Personally, for us who had grown up playing Super Mario, we've always wondered if there's a way for the Italian plumber to know whether a mushroom was poisonous or a power mushroom before he ate it. Thinking along that line, just like how there are poisonous mushrooms and power mushrooms in Super Mario for people to hunt, people hunt these mushrooms for consumption in real life as well. Yunnan, China is home to many mushroom hunters who gather mushrooms for a living, but recently there has been a sharp increase in mushroom poisoning outbreaks in the region caused by new species of poisonous mushrooms appearing in the region, with over 500 outbreaks and 28 casualties being reported. And globally, it's estimated that over 100 deaths occur each year due to poison mushroom incidents, many of which are caused by consuming wild self-picked mushrooms, but many are also caused by mushroom hunters selling poisonous mushrooms by accident. To help combat this issue, our group has decided to make a program that can separate poisonous mushrooms from edible ones. But how will we be able to do so? This leads us to our problem statement to investigate the identifiable characteristics of a poisonous mushroom and use machine learning models to predict whether they are edible. According to research done by Wild Food UK, many poisonous mushrooms actually have common distinctive features that can reveal whether or not they're poisonous. Therefore, we look for a dataset which contains the characteristics of poisonous and edible mushrooms. Begin. From our initial Kaggle dataset, we have provided 22 common characteristics of most mushrooms. All of them were categorical variables such as the color of the mushroom and whether or not its gill size was broad or narrow. Through initial analysis, we've identified that all the columns are categorical variables without missing any data. However, the data was difficult to decipher, so we first used the information sheet provided to rename the alphabetical features into more readable features such as K into black and Z into rhizophos as seen here, following which we sorted the data set into two sets according to whether they were poisonous or edible. Next, in order to calculate the proportion of poisonous mushrooms that has each characteristic of a mushroom, we first calculated the number of poisonous mushrooms and edible mushrooms that has each characteristic. We then made the function called proportion, which calculates the proportion of poisonous mushrooms for every characteristic using the formula poisonous mushrooms divided by poisonous plus edible mushrooms for characteristic. Lastly, we plotted all the counts of edible and poisonous mushrooms for each type of characteristic on a bar graph in order to visualize the data. Plotting all of it, we analyzed the graphs and statistics, picking out any proportion of a characteristic that is over 70%, narrowing down on these characteristics as more important identifiers of poisonous mushrooms as more poisonous mushrooms have them compared to edible mushrooms. This is the final list of important characteristics, ranked according to the proportions. Next, we use the K-Moods algorithm. K-Moods is a clustering algorithm that works with categorical data. The K-Moods algorithm works by iteratively assigning data points to clusters based on the similarity of the categorical values. It then updates the cluster centers based on the modes of the categorical values of the data points assigned to the cluster. The algorithm continues iterating until the cluster assignment no longer changes. To prepare the data set for a K-word analysis, we first used one hot encoding to give a numerical value to the categorical data before creating a K-word object using the Huang algorithm and 5 clusters. Next, we apply a decomposition method from sklearn called principal component analysis to reduce the number of dimensions, so we can create a scatter plot of the first two principal components. At the same time, we print the mode for each attribute for each cluster in order to visually represent all the K-mode data. The data circled in red showing the two sets of clusters and their modes, which shows the important characteristics of poisonous mushrooms identified using the Huang method. For our machine learning process, we use the decision tree and random forest classification models. For the decision tree model, we first divided the mushroom data into smaller subsets based on the values of its features and trained them to find what features makes a poisonous mushroom. We began by using 8 different depths and comparing their conversion matrices, Gini indexes, and true positive rates. The first decision tree has a Gini coefficient of 0.287 and 0.068. This indicates that older none is a very important characteristic. Using only this characteristic, we can largely distinguish between edible and poisonous mushrooms. However, this comparison is not accurate enough, so we added more depth to the tree to make predictions. When the depth is 2, the Gini of the child list starts to show 0.0. When the depth is 3, 4 out of 7 of the child list have a Gini of 0. This indicates that our accuracy is gradually increasing. As we reach deeper in depth, more and more the child lists have a Gini of 0, indicating that our model is approaching the highest accuracy. After multiple tests, the Gini values of depth 7 and 8 remain stable at 0. For the conversion matrix, you can see that depth 1 to 5, the true positive rate of our test data is gradually increasing, approaching 1. After depth 6, the true positive rate of our test cases remain mostly stable at 1. Then we found that depth 7 or 8 is the most suitable depth as the true positive rate for the test if 1. And because these true positive rates are the test cases, so we don't have to worry about the model overfitting. The accuracy of 1 shows that our model is very successful as it estimates predictions that are 100% accurate. Therefore, we use a decision tree with a depth of 8 to analyze the most influential characteristics for distinguishing between edible and poisonous mushrooms in this model. Next, we use the random forest classification model. We first use the one-hot encoder to convert the categorical to numerical data. Then we constructed a random forest with 150 decision trees. Here's the outcome analysis of our model. The ROC AUC score is the area under the ROC curve as shown on the right. This model gives a 99% accuracy rate, which shows that the random forest classification is effective in determining poisonous mushrooms. The top 25 most important characteristics as classified by the random forest is then shown here, nearly identical to the previously identified characteristics. We then further adjusted the parameters to improve our model. We used a grid of parameters for the model to randomly pick a trait. Using that, we created a base model before using the random grid to select the best model based on the ROC AUC score. This set of parameters make the model perform just slightly better than our original model. This is understandable because our original model already performed well, so tuning some hyperparameters might not add any significant improvement to the model. The next method we use to identify poisonous mushrooms from the bunch is an AI deep neural network machine learning technique known as the convolutional neural network. To gather data to feed our neural network, we sought over 400 mushroom images with classifications from the internet. However, we still require more images to train a proper model. Hence, we artificially increased the number of unique training examples by using the Keras image augmentation API to around 5,600 images. The convolutional neural network consists of 3 convolutional layers, each followed by a pooling layer, one fully connected layer, and an output layer with a single node outputting a probability value. The architecture of our model is visualized in this flowchart here. The convolutional layer are the major building blocks of the neural network. Each layer applies a convolutional feature to the input image, which produces a set of feature maps. We then use a 3x3 matrix filter to slide over the input image in a process known as convolution. And for every position, we will compute an integer which forms a single element of the output matrix, the feature map. In our model, the depths of our 3 convolutional layers are 32, 32, and 64, following which is the ReLU layer, which introduces nonlinearity in a CoffNet, and max pooling, which reduces the dimensionality of each feature map while retaining the most important information. Lastly, the dense layer receives input from all the previous layers and classifies the image, finally outputting a probability between 0 and 1 for whether a mushroom is poisonous. Here is the final result. The loss represents the differences between the predicted output and the true output, and the accuracy is calculated by dividing the number of correct predictions by the total number of predictions. The model will be trained for a total of 50 passes over the training datasets. During each iteration of training, the model will process and update its weights based on the 16 samples from the training dataset. The picture on the left shows the training and testing accuracy for each of the epochs. As the train accuracy reaches 85%, the testing accuracy will begin to hover around 80%. In order to put our AI and machine learning models to usage, for the AI model, the user can upload an image and the AI model will output a single value describing the probability of whether the mushroom in the picture is poisonous. For the machine learning algorithms, the user must manually input every of the 22 characteristics into the algorithm before our function uses the feed transform method to encode each input from a categorical variable into a numerical representation. The 22 characteristics are then inputted into the decision tree machine learning algorithm, which will return an output telling the user whether or not the mushroom is poisonous. Overall, both the random forest classification model and the decision tree model are good predictors of whether a mushroom is poisonous given a set of 22 characteristics, with 99% and 100% accuracy respectively. However, it is not as user-friendly as the convolutional neural network. The CNN AI model simply requires the user to input an image of the mushroom and can return the result with around 80% confidence level, while the machine learning algorithms will require the user to manually analyze and input 22 characteristics, easily allowing for human errors to occur. The K-mode and proportion method used to analyze the characteristics initially both manage to accurately identify the most important characteristics required to identify a poisonous mushroom as well, which can provide high practical knowledge usage, as mushroom hunters can use this to conduct a first-glance evaluation of mushrooms in time-constrained situations. All 3 parts of the project successfully did their jobs of identifying poisonous mushrooms, but each with their own perks and trade-offs, mainly between ease of usage and accuracy. For our takeaways, as our main issue for dealing with this dataset is that every characteristic is a categorical variable, most methods we learned in class cannot be used, and we have to learn new methods to deal with the variables, namely utility methods such as one-hot encoder, pipeline, K-mode, and feed transform. We also learn new models such as the random forest classification and the CNN. To end it off, while the theoretical data of our models for detecting poisonous models look promising, all of this is still based off of only one set of data from 2 families of mushrooms. A larger and more balanced dataset could be used to further improve on training these models. The accuracy of the convolutional neural network model used could have also been improved by a more complete dataset rather than augmenting images. We're also limited by the capabilities of our home computers to run larger epochs for better results. Therefore, adjusting parameters such as epoch num might have helped improve the AI's accuracy as well. Lastly, it is definitely safest to not eat any wild mushrooms, even if the algorithm provides a 100% reply that a mushroom is safe. Thank you for your time.